Okay, so good morning, everyone. I think I can still say that, can't I? So I'm a small angle instrument scientist here at the ISIS neutron and muon source in southern England. We're about an hour to the west of London and not far from the city of Oxford. And the group I work in now operates 3 SANS instruments and 1 spin echo SANS instrument. So ISIS is a spallation neutron source like the SNS at Oak Ridge, but we're lower power. We're about 20% the power of the SNS, but we have been around a long time. We commenced operations in 1984, so almost 40 years ago now. But unlike the SNS, we already have 2 target stations. As you'll be able to see from my Zoom backdrop, if we could turn the picture around 180, you'd see a 3rd generation synchrotron in the background. That's the diamond light source. So at our national lab, we've got neutrons and X-rays co-located on the same campus. So this session is about a software application called SasView, which, as my subtitle there alludes to, offers a number of options for analysing small angle, very small angle, or even ultra small angle neutron or X-ray scattering data. There is at least one person I know of that even uses it to analyse static light scattering data. He quite often asks us whether we're prepared to change the Q scale into inverse meters. So far, we've managed to resist him on that one. This is the outline for my session, both parts of it. I'm going to start by taking a moment to consider what we mean by data analysis. And Hans, in his opening presentation, laid some groundwork for me. Then I want to mention something which is actually very important, but which is often taken for granted, and that's the format of the data that you actually are trying to analyze. We'll then consider the analysis landscape that's available to you, at which point you'll hopefully learn why SasView just might become your best friend. I'll introduce you to the SasView collaboration, because SasView would not be what it is today without the contributions of a large number of people over several years. Facility scientists like myself, software developers, placement students, postdocs, and facility users like yourselves. If all goes to plan, the bulk of my session will be me doing some live demonstrations of SasView. So that'll be after lunch. And probably means that anything could and maybe even will happen. And then we'll wrap up with a question and answer. So I hope that sounds like a plan. So what is data analysis? Well, I did what everybody does these days. I asked Google and found these 2 quotes. The first is from that font of all knowledge, Wikipedia. The second from a rather more academic treatise on research integrity. Now, whilst the wording is obviously different, I've used some color coding to highlight that actually they both tell us the same thing. Namely, that data analysis is about learning something from our data through a process of interpretation, mindful that our data may have limitations. To which I would also add, and encourage you to always bear in mind, that process of interpretation may have limitations too. The 2 things are evident. First, we have to prepare the data we want to analyze, and second, we've got to identify a process for our analysis. As experimentalists, we need to remember that data analysis is the penultimate step in a data processing pipeline shown on the right, that starts with a neutron or an X-ray being recorded on the detector. We can only analyze the data from the sample and thereby extract useful information once anything of an instrument-dependent nature has been sufficiently corrected for. This correction procedure is what we refer to as data reduction, and it's quite distinct from data analysis. Now at the SNS, and I think HIFA 2, SANS data reduction is invested in the Manted framework. We use Manted at ISIS 2, as do a few other facilities. If any of you have used the NCNR at NIST, then I think data reduction there still uses scripts in Wavemetrics Eagle. So data reductions where things like the efficiency and spatial response of the detector, the electronic background, the masking of pixels, accounting for the sample transmission, the beam size, and the sample background, things like that all get corrected for. The data coming into data reduction is variously called live, or raw, or unprocessed, and probably a few other things besides. At the SNS and ISIS, this raw data is stored in the form of Nexus files, and we'll learn a bit more about those later. The data we're going to analyze, however, coming out of data reduction is what we call reduced data. And reduced data should be completely instrument independent to the extent that it can be directly compared with reduced data measured anywhere else. And to prove this point, here on the left, you can see a series of measurements performed on the same material at 4 different reactor SANS instruments, 2 at NIST and 2 at the ILL in Grenoble, France, on my pulse source SANS instrument, and on a USAC beamline at the APS. And I'll hope you'll agree that's pretty good agreement. These data were part of a reproducibility exercise that a network of SANS and SACS facility scientists called Kansas, that Lillian mentioned in his introduction, conducted a while back, and you can find further details on the website shown. The other thing to remember is that in small angle scattering, the intensity axis not only has units, it can be put on an absolute scale with a suitable calibration sample. Or conversely, such a sample can be used to check that the reduced data has, in fact, been suitably corrected. So when you go to do an experiment and your instrument scientist tells you at the start that they're going to take an hour to do a calibration, now you know why. It's to your advantage. Over the years, as IT technology has improved and as experiments have got more sophisticated, reduced data formats have adapted and evolved. Now, at first thought, this might seem strange. You might be thinking, how complicated can it be to store a bunch of Q values and intensities? To which the answer is not very complicated if that's all you want to store. However, the reality, as you can see here, is that the actual scattering data is but one element of a potentially much larger set of information. The more of this set your reduced data file contains, the more value it has now and in the future. And increasingly, funding agencies, your institutions, and even journals are requiring the deposition of data so that it can be checked, shared, and even reused. This is the concept known as open data. So the days of a reduced data file being nothing more than 2 columns of numbers have all but gone, except for your own personal use maybe. So what are the options for storing reduced data? Well, broadly speaking, there are 3 categories. The first of these is hopefully self-explanatory. It's certainly straightforward to produce and it's simple to inspect. But these minimalist formats are, if you like, the lowest common denominator of the data format world. And beware comma-separated variable files, CSV files, because in some cultures, though admittedly not in North America, the computer language settings can sometimes substitute the comma with a semicolon. And that's a pretty good way to bamboozle most file loaders. Or another foible is that the language settings introduce a comma to separate the thousands in numbers, and then the file loaders end up looking for way too many columns. Moving up a step, we have the self-describing formats. And the way you can think about these is that they describe their data in much the same way that HTML describes the content of a web page. Indeed, the XML that you see there stands for Extended Markup Language, and I'll show you an example in a moment. The Achilles heel of XML, if you want to use it properly, is that whilst validating the file structure is obviously a good thing, The schema, as it is called, that does the validation is external to the file. In addition, XML can seem rather verbose, but it has a lot to commend it. The hierarchical formats take the self-describing concept to the next level and are truly portable. As I've said on the slide, you can think of these as file systems in a file, with different pieces of information in different folders. This is the most efficient format for voluminous reduced data, but at the price that you need a compatible program to inspect the file. Now, SasView will read data from all three of these categories, but please note that is not the same thing as saying it will read any reduced data file you throw at it. Now, there are two formats I particularly want to mention. If the word Kansas looks familiar, that's because we encountered it earlier when I showed you the graph of round-robin data from different facilities. In addition to pursuing the concept of standard samples, one of the other things the Kansas network has pushed is standard data formats. The Kansas 1D format is now reasonably well established, and I think I'm right in saying that at least one manufacturer of laboratory X-ray machines has adopted it. It is an XML-based format for 1D data only, so just intensity against Q. NX Kansas is our new kid on the block. It's a hierarchical data format to what's called the HDF5 standard. Whilst it can and is used for storing 1D data, it really comes into its own when you want to store 2D data or multi-dimensional data and or lots of non-neutron data alongside the neutron data. To save reinventing the wheel, we decided to adopt some of the structure found in the Nexus raw files, because Nexus is another HDF5 format. So NX Kansas is in fact a subset of Nexus, hence the NX prefix. The principal difference between the two formats is that Nexus is primarily used to store raw data, whilst NX Kansas is only used to store reduced data, and that allows us to do away with some baggage. So let's take a look at some of these formats. Hopefully you're seeing an editor now. If not, somebody please shout. So I'm going to show you the same data, but in some different formats. This first format is just 2-column data. Okay, there is absolutely nothing else in here other than 2 columns of numbers. We don't even know what those columns are, but we assume one of them is Q, one of them is intensity, and we're probably also assuming that the first column is the Q. If at some point that file gets renamed, or you hand it over to a colleague and they change the name or something like that, you have no idea what this data is. There is no what we call metadata in the file. So this really isn't a good format. Here's another minimalist format, but this one's a little bit better. It not only tells us when the file was generated, it's telling us which instrument the data is from, it's telling us what sample this data is from, it's telling us how many points are in here. If anyone is old enough to remember Fortran, there's even a Fortran format specifier in there, which means that a data analysis program could use that to work out how those 3 columns have actually been written into the file. And now, again, it still doesn't tell us, but we have a column of Q values, a column of intensity values, and a column of uncertainties on the intensity values. So this is a step up. Next level up is to take the same file, but now add in a 4th column. And the 4th column now is the uncertainties on the Q values. If you can have reduced data with 4 columns, that's what you want. So those were the minimalist formats. Here's the same 4-column data, but in XML. So you can see that the data is now wrapped by these XML tags, but it's still very readable. But now it actually tells us that this first column is Q. It tells us that the second column is intensity, that the third column is the uncertainty on the intensity, and so on. Not only that, it also tells us what units the values that we're seeing are. But there's much more information in this file. Excuse me. If I scroll down, once we've got past the intensity and Q data, we find there's then a block of data which is actually giving us the wavelength dependent transmission of this sample, again, along with its uncertainties. That's because this data was generated on one of our time of flight SANS instruments. If we keep going down, we then have the transmission information for the container that was in. Now, whilst you don't need this transmission data to do the data analysis, it's nonetheless very useful as a diagnostic if you start to see strange scattering plots. And then right at the bottom, we have some more metadata, which not only tells us which data reduction program generated it, it tells us which version of that program, which configuration file that we used in mounted, and it even tells us what run numbers from the instrument we used to actually generate it. So there is an awful lot of very valuable information in this particular version of the data. Because it's XML and it's describing how the data is packaged, it doesn't have to look like this as long as it still conforms to XML. So I'm now going to show you the same data in XML, but looking somewhat different. And that's one of the beauties of XML. If we look at the same data in the hierarchical format, it means nothing to us. And that's because the hierarchical formats are actually binary. So if I'm opening them in a text editor, it makes no sense to me at all. It's not what we call human readable. And that's the disadvantage of the hierarchical format. You can't open it in a simple editor and inspect the values. Instead, you need to have a program to do that. One such example of that is this program called SasView, which was initially developed by the National Centre for Supercomputing Applications. It's Java-based. So if I load in a hierarchical file, okay, there's the top level, and it's saying there's an entry in there. If I expand that entry, I then find beneath it, rather like having subfolders, is all the information that we're looking for. If I go into the one for SAS data, sorry, it brought the pop-up window on a different screen. There you go, and you can actually see the intensity values. All right. So the disadvantage of the hierarchical files is you need another application to actually see what's in them. So what about the options for small angle scattering data analysis? Well, the fact is, because small angle scattering is a very mature technique of use to a very diverse community of science. I know most of you listening are soft matter scientists, but the appeal of the technique goes way beyond us. And it generates data with a wide range of information content, as Otto was showing earlier. Sometimes the scattering curves look relatively smooth, and sometimes, they almost look like crystallographic diffraction patterns. It means a number of very different methods for analyzing small angle scattering data have emerged over the years. This graphic, and you can find an extended version of it on our website at the link shown, tries to summarize some of those methods available to you. So Otto's been talking about real space methods. I'm going to be talking about model fitting methods. It might look a bewildering landscape, but not every method is appropriate for every experiment. And even where more than one method can be used, the golden rule is always to start simple. Otto would say, start with PDDFs. How to know which method or methods to use depends on a number of things. Top of the list, of course, is what you actually want to know from your data. If you're just after a radius of gyration, then you might be able to get away with putting a straight line through a Guinea plot. But if your goal is the tertiary structure of a protein, you're going to find yourself doing a lot of ab initio or molecular dynamics modeling. The factors such as the field you work in, or even the statistical quality of your reduced data, may also have a bearing on your choice of method. For example, methods involving the mathematical transformation of the reduced data from Q space into real space typically demand higher quality data over a wider range of Q than model fitting does. On the other hand, structural biologists are encouraged to deposit atomic coordinates for their structures in public databases, and those can only come from advanced modeling methods. So at the end of the day, your choice of method or methods will probably be guided by your advisor, by your colleagues, and the literature you're reading. As we saw from Otto's talk, some of these methods are model-free, others require starting structures or some intuition about the shape of what is responsible for the scattering. Model fitting, that is the iterative comparison of an analytical calculation to the reduced data by means of the optimized variation of the model descriptors, is far and away the most common, most used method of SAS data analysis, particularly in soft matter science. There are a number of model fitting programs available, each of which has its pros and cons. But as we heard earlier, none of this means that model fitting is necessarily the best method. It is a method that's available to you. At its core, SasView is one of these model fitting programs, and that's where I'm going to spend the majority of the remainder of my time today demonstrating. However, it does perform some other types of data analysis. But by design, SasView does not perform ab initio or Monte Carlo or molecular dynamics modeling. And the reason for that is quite simply that there is other well-established, very capable software out there to do these. For example, the SAS suite from the European Molecular Biology Laboratory, work of Dimitris Fergan, and SASI out of NIST, the work of Joseph Curtis, are two leading examples. So SasView doesn't do the ones I've just put a red cross on, it does do the others. Before I move on, I want to tell you something about the SasView collaboration. The origins of SasView lie in a very large and forward-looking NSF-funded software project called DANCE, Distributed Data Analysis for Neutron Scattering Experiments, that was led out of Caltech. And it's no coincidence that software development proceeded alongside the commissioning of the first instruments at the SNS. Back then, the SANS component of DANCE was known as SansView. But when DANCE ended, a new mechanism for continuing to support the development of SansView was needed, and that mechanism was to turn it into a community software project under the stewardship of Paul Butler at the NCNR, whom some of you may know. Paul had been the principal investigator for SansView in the DANCE project. But so as not to alienate any potential collaborators in the X-ray community, the decision was taken to drop the N in the name, and so SansView became SasView. As of now, something like 40 people from the 9 organizations whose logos you see at the bottom of the slide have contributed to making SasView what it is today. In any one year, there's typically 12 to 15 active contributors. But in its history, there have been very few full-time software developers working on SasView. Most contributors are only able to donate a few hours a week to the collaboration and are not necessarily dedicated software developers. Now, people like myself, for example. These contributors meet on Zoom every other week, but also try and meet up for an extended period, at least once a year, either for face-to-face co-camps in exotic locations, as you can see from the photographs, and you should hopefully recognize at least one of those locations, or for a virtual hackathon, which is something we had to invent during the pandemic. And typically we use these gatherings to progress bigger chunks of work ahead of a new release. All of the SasView source code is publicly available, it's open source, and it's released under a permissive license. And this transparency is intended to promote confidence in the software. It's not a black box like some other analysis programs. We follow, as far as we can with our limited resources, industry best practice. So we use GitHub for hosting the source code and for bug tracking. We employ unit tests, And we have automated build servers for Windows, macOS, Ubuntu, and there's even a third-party project in Australia implementing SasView on Debian. We also have a model marketplace where SasView users like yourselves can contribute new or modified models, which can then be downloaded and immediately implemented as plugins by other users. Most of the program is written in Python, with some of the under-hood routines in C for speed. The GUI uses PyQt and the graphics are matplotlib. Each release gets tagged in GitHub and assigned a DOI. So not only can you cite a specific release of SasView when you're writing your paper, but you have the assurance that the source code that generated a particular result from your reduced data will always be fully traceable. We've tried hard to make SasView accessible and usable, particularly to those new to small angle scattering or new to SasView. Indeed, in the last 10 years, SasView has been referenced in almost 500 peer-reviewed publications, so we must be doing something right. The program comes with quite extensive user documentation, available both in program and online on the SasView website. The website also features an FAQ page. Many of the questions that appear there are ones that SasView users have asked. So together with the documentation and the FAQ, they are a very invaluable resource. Beyond these, we have Slack and Twitter channels, though I have to say they're not terribly active, and 2 support email addresses, help and users. One asks the development team, the other asks SasView users. We have some illustrated tutorials on the website, which take you through some of the more common operations in SasView and which you can follow along using the test data that we supply with the program. There are actually more tutorials now than you see listed on the slide. And we even have video tutorials on YouTube. If any of you would like to contribute your own tutorials illustrating particular uses of SasView, then please do get in touch. Last but not least, we do occasionally participate in relevant scattering schools, workshops and courses, as you're experiencing today. Clearly, though, we don't have the resources to do as much of this as we would like, but fortunately these days there are some technological alternatives. You see here the Pan Learning website run by 2 European open science projects. This is an e-learning platform where you can take self-paced instruction in different courses. Neutron scattering is actually quite well represented. And there is a Moodle-based course on SasView that was put together for us one summer by an ISIS sandwich student. A sandwich student in Europe is what you would call a cooperative student in North America. So as I hope you now appreciate, SasView is very much a community endeavor because the science that you do guides its development. And if you're willing and able to give back by contributing to that development at some point in your careers, that would be truly awesome. Before I actually demonstrate SasView, I thought it might be helpful to say something about model fitting, which is, after all, the core function of the program, particularly for those of you that are perhaps new to data analysis. So I've put a few slides together I've called Model Fitting 101. In its simplest possible terms, model fitting is about finding a physically realistic model that accurately describes the data with a physically realistic set of parameters. That last point is overlooked more often than you might think. There have been many occasions where users have triumphantly sent me tables of parameters from their fitting endeavors, only to have me point out that their dilute dispersion had a volume fraction beyond the close packing limit, or their shell thickness was smaller than a carbon-carbon bond. The way to ensure physical realism is, of course, to draw upon as many other sources of information about your sample as you can. It's what mathematicians refer to as using a priori knowledge. A priori being the Latin for from earlier. And you heard Otto mention it in the previous talk. Another common misconception is that more parameters in a model means it's a better model. It might be, or it might not. But a model with more parameters will certainly be more complicated and harder to control. And whilst fitting engines will do their level best to find you a good solution, asking them to optimize too many parameters too soon is generally a bad idea. This is why. And you've seen a variation of this picture already. You see, you can think of your fitting problem like a potential energy surface, but instead of energy and distance between objects, we have some measure of the fit quality, let's say the chi-squared, as a function of our parameter values. And what you're seeing here is just a two-parameter problem. The best solution to the problem is located at what's called the global minimum, the deepest point. But as the fitting engine varies the two parameters looking for that global minimum, you can see that it might easily find any one of the local minima and give you that solution instead. Now, different optimizers, fitting engines as they're sometimes called, are more or less susceptible to this. In general, you can have a fast optimizer, meaning it will find a minima quickly, or you can have a robust optimizer, meaning it is more likely to find the global minima. The fast optimizers effectively scour the parameter landscape, trying to find locations that are not flat. The robust optimizers conduct much more elaborate searches, sometimes learning as they go or by employing probability theory to guide where they search next. Some methods are just like dropping paratroops on a landscape and asking them to radio back in their altitude. And obviously these days there's an increasing interest in what artificial intelligence might be able to do in this area in the future. SasView actually has a suite of 5 optimizers that span these different approaches. The fastest optimizer in SasView, and the one that's the default optimizer when you first start the program, is called the Levenberg-Marquardt, or LM for short. It's widely used in model fitting packages. In fact, you'd probably be hard pushed to find a model fitting package that didn't have a LM optimizer. It's very good for zeroing in on possible solutions, but because it's prone to finding local minima, you may need a more robust optimizer for more complex models. The most robust optimizer in SasView is called Dream, but it's much slower. All of the optimizers in SasView hail from a package called Bumps, written by Paul Kinzel at NIST. If any of you are familiar with the REFL 1D program for fitting reflectometry data, that also uses Bumps. So that concludes my slides for the moment. I guess probably a good thing to do at this point is to actually show you where you can get SasView from. So this is the SasView website, 3ws.sasview.org. And here, front and center of the page are 2 big buttons. At the moment, we actually have 2 slightly different releases of SasView. And the reason for this is that the version 4 series is built with Python 2 and the version 5 series is built with Python 3. And any of you that know anything about Python will be aware that Python 2 has reached end of life and is going to be, it's already deprecated and it's going to be phased out. So we're not actually doing any active development on version 4 anymore. All our development is going into version 5. And to obtain the program, you just need to click on the button, which will take you to GitHub, where you will find some release notes which tell you what we've changed in the latest version, what things we've fixed or added in. As it turns out, there were quite a few in that last release. There's some additional information, and when you get to the bottom, you can actually find some installers. Okay, for both Windows, Mac, and Linux. If you need a specific version of SasView for some reason, that the only reason I can think of these days would be if you happen to be trying to use a 32-bit machine, whereas most machines these days are now 64-bit. you can go into links and downloads, and down here you see there's a link to all versions from version 3, so you can actually obtain a specific version of SasView there. I talked about the model marketplace earlier. So this is at marketplace.sasview.org. And there's quite a few models here. Not only are all the built-in models on SasView available here, but then there's also models that other people have contributed. A red cross means that the model has not been verified or checked by the development team, so you kind of use it at your own risk. But since the person that put it there is identifiable, it's kind of in their own interests not to put rubbish up. So you can be reasonably confident the model will at least do something like it ought to be, something like it claims. Back on the SasView website, the documentation link here, you can access online all of the help documentation for the different versions of the program, but we do ship that documentation with the program. So you don't have to be connected to the internet to read the documentation. If you go in there, under user documentation, probably the most important thing in here is the model documentation. These are all the models that are built into SasView at the current time. When we can find the time and the people to do it, some of those models that you just saw on the model marketplace will probably get added to this list. And for each model, pick something that might be vaguely familiar to you, the sphere, because Otto talked a lot about sphere. It tells you what parameters the model will have. It will tell you how the model has been defined, and it even throws up a picture of what the function actually looks like. So that's a very good resource there. The other links on here will tell you about how to use the program, or the other types of analyses that are actually available in the program. Because SasView doesn't just do model fitting, it will do the sort of analysis that Otto was talking about earlier, and a couple of others besides, and I will try and demonstrate those to you after lunch. It tells you about some of the other tools that we have available. And it actually tells you something about going further with SasView if you need to. So I think I'm going to stop there, and we'll call that lunch, I think, if that's all right, Lily.
Yes, unless someone has a quick question.
Yes.
Any question for Steve? Otherwise, we can have a lunch break now. So we come back at 1 o'clock. How about that? So we should have a lot of questions for Steve during his second part of the talk. Okay. I will see you at 1 o'clock.
Okay, thank you.
Bye-bye.
data analysis of small angle scattering data from soft materials. And this is the second half of our workshop. If you participate the first half this morning, you know we have Dr. Stephen King with us today. Dr. King has over 30 years of experience in small angle neutron scattering of soft materials. He's a world-renowned scientist with numerous publications. He's involved in the development of the SasView software. And this morning, he gave us an overview of the SasView software. And in the second part of this, his lecture is going to give us a demonstration of SasView. Steve, I'm going to hand it over to you.
Thank you very much, Yang Yang. Could you confirm you're now seeing SasView?
Yes.
Good. Okay, welcome back, everyone. So in this half of my session, I'm going to basically do stuff in SasView. It's going to be a whistle-stop demonstration of its capabilities, I'm afraid, but pretty much all of the example data I'm going to use is from the test folder that ships with SasView. So if you download the program and install it and then play back the recording of this session, you'll be able to practice what I'm about to show you. So when you run SasView, this is what you'll see. So we have a conventional toolbar up the top here. If you prefer icons, you can do view, show toolbar, and you'll get some icons. Equally, you can clear up some screen real estate by hiding things if you want. On the left, we have what we call the Data Explorer, and this is where the reduced data that you load into the program will appear, and also where some derived data that the program calculates will also appear. At the bottom, this Log Explorer is effectively a message area. You can increase or decrease its size. So if you get an error or a warning or something like that, that's where it's going to appear down there. And because SasView is primarily a fitting program, it tries to be helpful, and it creates this thing that we call a fit page. So the first thing we want to do is we want to put some data in there, and there is various ways of doing that. You can either use the conventional file button and you can load individual data files, or if you want, you can load an entire folder of data. You also have the option to load a project or load an analysis. The difference between those is that if I have just done let's say I've just done a complicated fit to a particular data set, I can actually save the current state of SasView with the data and all the parameters and everything like that. I can save that to an analysis. If I have several fit pages I've created or something like that, then I can save that as a project. That's the essential difference between them. So, and the other way of getting data in, of course, is you can just click the big load data button there. But let me demonstrate load a data folder. So here's a folder. And you can see some data sets have appeared in the Data Explorer. These are the same data sets I showed you in the first half of the session, where I was talking about different file formats. Okay, now you'll notice that 3 files there have got the same name, so the program has had to stick a number in brackets after them to differentiate them. And that's because it's read some metadata from inside the file, and it's tried to be helpful by actually telling us what the data is rather than just giving us the file name. But of course, in this instance, it's actually unhelpful. But the nice feature is that we can right click on the data set and we can do change name, and then we get some options for how we actually want to address this file. So what I'm going to do is I'm going to turn all these into the file name, because then it's going to be easier to identify what they actually are. There we go. All right. And then there's a combo box here that lets you, is capable of sort of filtering some of these files and either selecting them or unselecting them and things like that. So I'm going to unselect them all. And then I'm just going to select the 2-column data. And you remember, this is the worst of the minimalist formats, okay? And then I'm going to send that data to fitting. So its name now appears up here in the fit page. Now, this particular sample is a partially deuterated polystyrene blend. And if anyone from Oak Ridge is listening, it actually has some history here because it was given to us by none other than George Wignall, GDW being George's initials, of course. But we still use it now and again. So it's a polymer dispersed in itself, if you like. So that's kind of as good a solvency conditions as you can have, and so we would expect this to exhibit Gaussian change statistics, and so the scattering from that is described by the Debye Gaussian coil. So I'm going to go into my model categories here. I'm going to choose shape independent. These categories, incidentally, are we've come up with a default categorization, but you can actually go into a category manager and completely reassign things if you want. So if there's only a handful of models that you ever use, you could create a new category, call it My Models, and just put in the models that you own, that you use for your analysis. You don't have to stick with these ones you see. So I'm going to go into shape independent, and then here's the list of models that is actually available under the shape independent category. And you saw these earlier when I showed you the website and I showed you the list of models. There are 2 Gaussian coil models in here. There's one for monodispersed polymers and there's one for polydispersed polymers. So I'm going to choose the polydispersed, and up come the parameters for this model. All right. Now, I actually have a little bit of a priori information here, and that is that I know the polydispersed of this polymer is 1.09. So I'm going to set that. And let's have a look at the data and the model calculation. So 2 graphs appear. The first one is showing us the experimental data as the markers, the blue markers, and the calculation of this model based on the parameters you see over here is the orange line. Obviously, at the moment, it doesn't look much like the experimental data. We have some limit bars here that allow us to adjust the range that we actually want to do the fitting over. You can either drag those bars to select your Q range, and then you see here at the bottom of the fit page, you'll see those numbers change. Otherwise, you can go into fit options and you can just type numbers in those boxes, hit return, and it'll move the error bars for you. The other thing I'll point out for this data set is because it only has 2 columns, remember it only has Q and intensity, we have no intensity weighting scheme. The other graph it's put up is a plot of the residuals as a function of Q. That's showing us how far off the experimental data the calculation is. And obviously what we want to try and achieve is a horizontal line bumping around 0. So we have a little way to go at the moment. So we can now think about doing some fitting. So I'm going to ask it to fit the background level. I'm going to ask it to optimize the intensity at Q equals 0, and I'm going to ask it to optimize the radius of gyration. And then I'm just going to click fit. And there we go, it's done a fit, and you can see the residuals plot is now kind of hovering around 0. So we've done a reasonable job. I then look at my parameters and I go, yeah, I happen to know that something just over 70 angstroms for the radius of gyration is about right. And if I wanted to, I could take that I0 value, and because I know what this polymer is, it's polystyrene, I can calculate the scattering length densities of the D and H polystyrene, and knowing that, the bulk density of the polymer and that I0, I can go off and I can calculate the molecular weight. But you'll notice that although it's done a pretty good job of fitting the low Q here, it's not done such a good job of fitting the high Q out here. And The likely reason for that is because the fitting program is actually trying to pay the same amount of attention to every data point in there. That's not really what you want it to do. What you want it to do is to actually take account of the uncertainties. But of course, I said we don't actually have any uncertainties here. But we can simulate them down here. And I'm going to say, take the intensity value, take the square root of it, and assume that that's my uncertainty. Now, that's a kind of a get out of jail free card. It's not perfect, but it might get us somewhere. And the reason it's not perfect is that what that means is that at low Q, where your intensities are highest, you're going to have big uncertainty, but at high Q, where your intensities are smallest, you'll have small uncertainty. And if you look at a real experimental data set, that's not usually how the uncertainties are distributed. But as I say, this is a kind of a get out of jail free card. So having checked that box, let's see what happens. We'll just go back to the parameters. Let's see what happens if we click fit. There you go. See, it has actually improved the fit. It's made a small change to the parameters there. So only having 2 columns of data, not really what you want. You want more than 2 columns. 3 is a minimum. So let's have a look at the 3 column. So select 3 column data. I'll send that to fitting. It creates a new fit page. So now I'm going to recreate the model. Oh, hello. Font size has changed for some reason. Weird. Might be because I'm in Zoom. It doesn't normally do this. So there's the model again. I'm going to put my prior in. Okay, and I'm going to do exactly the same fit. Sorry, let's minimize those. So let's show this new data. Here's the new data. You can see immediately the residuals plot looks a bit different, and you can possibly also make out, particularly if I move that limit, you can just about see some error bars on the points down there, and you can see there's an error bar out here on the high Q. Right, and that's because we're now looking at a 3 column data set and it has the DI information. And we can check that if we go into fit options. And there you are. It says I'm now using the uncertainties on the intensity. So if we do a fit, straight away we get a pretty good fit over the whole Q range. We can then do the same thing with the 4 column data. I've got several options. I can pick any one of those files there. They've all got the same data in, remember, they're just a different version of it. I'll use the hierarchical one, why not? I'll send that to fitting, creates another fit page. I'll recreate my model again. Put my prior in. Let's minimize these. Show the new data set. Doesn't look any different to the one that we saw for the 3 column because we don't plot the uncertainty in Q. We'll fit the same parameters. And we get a slightly different plot again. Okay. And if I step back through these fit pages while you watch the parameters that are in here, oh, sorry, the reason it looks slightly different is that box didn't fit. Let's do it again. There we go. So if you watch the parameters while I step through the fit pages, you can see, I'm sorry, I don't know what's going on with the font size, but you can hopefully see that those parameters are all subtly different. And that's the point I want to get across here. The more information you have in your reduced data file, the better your fit is going to be and the more accurate your fit is going to be. Having done this, we could, if we want, of course, now go and save this out as a project. So I can give it some project, for example. and it gets saved, and then I won't demonstrate it, but I could close SasView down, reopen it, load that back in, and I would be back where I am at the moment. Some other things I'll just show you to do with plots. If you right click on a plot, you get a context menu. So here you can save the plot as a graphics file, or you can send it to a printer, or you can copy it to the clipboard to paste into PowerPoint or a Word document. You can annotate it by adding some text. You can toggle the legend on and off. Change scale. Somebody asked me a question in the chat earlier. In here, you can change the functional form of the data if you want. So if you really want to see it linear or Guinea, for example, there we go. If you want to change the limits on the axis, that's under set graph range. You can even change the title of the window if you want. Toggle navigation menu brings up the actual matplotlib navigation menu. And one nice thing about this is over here in the bottom right hand corner, it gives you the X and Y coordinates as you move around the plot. So if you want to, it's a very quick way of finding out where a point is in Q or what its intensity is, which can be quite useful. You can also do things like zoom in. So this is a Guinea plot, so we're kind of looking for a linear region in there somewhere. Right. You can pan around. If you get completely lost, just click the house icon, and that takes you back to where you were originally. Again, I can toggle that off. There we go. Now you'll notice that in the right-click context menu, the two data sets that we actually have on there, one is the experimental data set, remember, and the other is the model. They appear, and as you hover over them, you get an additional context menu. Data info shows you any metadata the program knows about the data, and it shows you the actual numbers in the file. You can remove a data set from the plot if you want. If you want to change the shape of the markers or the color of the markers, that's under modified plot property. Lillian asked a question about how do you, having linearized your plot, how do you get the parameters like the slope? Well, the way you do that is with the linear fit. Okay. So that's a kind of a quick introduction to some simple fitting. Let's go a step further. So all we fitted here is form factors, the P of Q. And you remember Otto was telling us about structure factors as well. Excuse me. So let's find some data that has structure in it. So this data set is from a 2% solution of the anionic surfactant sodium dodecyl sulfate. So at 2 weight percent, it's I think about 10 times the critical micelle concentration. So we can be guaranteed of having some micelles in here. As many of you will know, we can, to a first approximation, we can say these micelles are going to be spherical. So I'm going to choose the sphere category, and then I'm going to go find a sphere model. So now we have some different parameters to what we had for the polymer data I was just showing you. And again, I have some priors. And the priors I know that the scattering length density of the polymer is about 0.33. And it's in D2O, so that's going to be about 6.3. So let's see what things look like. There we go. I don't think I need to fit all this noise right out there. Let's bring it into somewhere around there. Of course, the region you choose to fit, of course, is entirely subjective. And then we can fit a scale, a background, and the radius. Now, in this particular model, the scale is actually equivalent to the volume fraction. So I'm going to go fit. Okay, it's done something, but clearly we need to go further. And of course, what we need to do, we can see that we've got a peak in here, and that peak is the interaction structure factor coming in from the fact that these are charged micelles in water, and so they can feel each other at some distance that's bigger than their radius. So what we want to do is to multiply our P of Q by a structure factor, and we have some options for different structure factors. And the one I'm going to choose for this system is, Otto called it the RMSA. This is a slight variation of it, also known as the Hayter-Penfold structure factor. I think I shall minimize the log explorer because we need more room. Yeah, there we go. So you can see we've adding in the structure factor has added in this bunch of parameters down here. So now I have some additional priors that I can enter. So it's in water. So I know that the dielectric constant is 78 at 298 Kelvin. Okay. Charge here is the charge on the micelles. I have no idea what the charge on the micelles is. I'm just going to leave it at that value for the time being. One of the things we can do here, you'll notice that we have a radius in here from the form factor. So that's the radius of the micelle, but introducing the structure factor has brought in this radius effective, which is the distance over, which is the radius of the micelle plus the Debye layer around it. Okay, and we have a choice of whether we actually want to couple those two together or leave them separate. And by default, the program has actually coupled them together, which is why the radius effective is in italics, and that's being set by this combo box here. Okay. If I choose unconstrained, then I would have to optimize the two radii separately, but I'm going to leave them tied together for the moment. So if I change radius, radius effective will change. So now, because we got the structure factor, that's actually introduced a volume fraction parameter. And because we've now got a volume fraction parameter, I no longer need scale parameter to do that. So I'm going to turn off optimization of the scale parameter, and I'm going to set it to 1. Okay, and I'm going to bump this up a bit. Optimize the volume fraction as well, and let's see what happens. Oh, how about that? You can tell I've done this before. Okay, it's still not perfect fit. You can see we're not quite, we're slightly overestimating the intensity in the low Q part down here. So what happens if we play around with the charge? Okay, that did improve things a little bit. Still not perfect, but it has improved things a bit. Of course, in reality, we would have to ask questions like, how confident can we be that the scattering length density of the micelle is still 0.33? There may be some solvent penetration into the shell, for example, which might up that. We might even want to explore whether the micelles are truly spherical. Don't have the time to do all that sort of thing, but you can see that it is possible to fit a form factor times a structure factor in here and obtain useful information from that. Something else I'll just demonstrate is, once you've got model fits to your data, you can actually that data is then available to you over here in the data explorer. So if I just go back to the polymer data, so we fitted the 2-column, the 3-column, and the 4-column data, and you can see that the models are now available over here. So if I want, I can choose the experimental data. So let's choose the experimental data, and then the 3 model fits to it, and then down here in the bottom left corner, I can go create new. It'll create a plot, and there's that polymer data with actually the 3 fits in there. And then again, if you want, you can save that or print it, copy it, whatever you want to do. Along similar lines, when you fit form factors and structure factors, those are also available to you. So I can actually get a plot showing me the contributions from both the form factor and the structure factor. And again, I can write those out as a file if I want. So all that information is available to you. Okay, what should we show you next? All right, so far we've only fitted individual data sets, okay, but there are many occasions where you might have groups of data sets or very many data sets. So let's address that. So the example I'm going to do now is from a water in oil microemulsion system. So it's water in cyclohexane. And what we've done is we've done the classic small angle neutron scattering experiment. We've done 3 contrasts, what we've called the core contrast, the drop contrast, and the shell contrast. So what we could fit each of those independently, but if we think about it, actually, the structure of what's in those 3 samples should be exactly the same, unless something really funny is going on. So really what we would like to do is to fit one model across the three data sets, and that's called simultaneous fitting. So what I'm going to do is send those data sets to fitting. Actually, before I do that, let's clean things up here a bit. So I'm going to unselect everything, select all, keep all microemulsions and delete everything else. There we go. I can select everything, send that to fitting, and I've only got 3 fit pages to worry about. So the model we want to fit here, so it's a water droplet stabilized by a surfactant layer. In this case, the surfactant is aerosol OT, and it's dispersed in an oil phase. So we've got a thin shell around our water droplet. So the model we want to fit is what we call a core shell. So we're going to find that in the sphere category, core shell. Okay, I'm going to do that for each of the fit pages. So sphere, core shell. And now I'm going to put my priors in. So fit page 5, it tells us is the core contrast. For the core contrast, well, my core in this case is D2O. So scattering length density 6.3. I only have hydrogenous surfactant. So that's got a scattering length density 0.62. And in this case, the bulk medium is hydrogenous cyclohexane at -0.28. Fit page 6 has got the drop contrast. So now the core is light water. So scattering length density 0.55. It's still hydrogenous surfactant at 0.62. But now my bulk medium is deuterated cyclohexane at 6.68. And lastly, fit page 7 has got the shell contrast. So my core is D2O. My shell is still 0.62. And my bulk medium now is deuterated cyclohexane again. So that's my priors. Okay. So what are we going to try and optimize here? Well, we're going to try and optimize the volume fraction, the background, the radius, and the thickness. So scale, background, radius, thickness. Scale, background, radius, thickness. Now, rather than go off and click the fit button on each of these individual fit pages, I'm going to go up here to fitting, and I'm going to choose constrained or simultaneous fitting. That creates me another page. I can click on one of these data sets, hold the shift key down, click on the last to select them all, right click, and I can choose neutral constraints. And this is where I can tie parameters between the fit pages together. Okay. In this version of the program, it only lets you tie 2 together. We're changing that so that you can do more complex constraints. And the way this works is the left-hand side is the child that is learning from the right-hand side, which is the parent. Now, sometimes you might want to think carefully about what you use as the parent. In the interests of time, I'm just going to go with whatever is in fit page 5, which of course will be model 5. So to start with, I will tie the scale together, because what I'm going to say is I'm such a good chemist that I've managed to make the volume fraction in all 3 samples exactly the same. Whether that's true is another matter, but we'll start with that. And I'm going to say tie model 6 scale to be the same as model 5 scale, add, and then do the same for model 7 to be the same as model 5 scale, add. I'm then going to do the same for the radii. And I'm going to do the same for the shell thickness. So I've now got 6 constraints. I'm going to ask the program to optimize this model to find one solution that ties that will fit the 3 different contrasts, but with the same volume fraction, the same radii, and the same shell thickness. So I'm just going to close this down. I'm not going to tie the backgrounds together because I've got some samples that are in a deuterated medium and some that are in a hydrogenous medium. So the background levels are going to be different. I'm going to let those float. And then I'm going to click the fit button here in the simultaneous fit page, not on the individual fit pages. A whole bunch of graphs are going to appear. Okay, so I'm going to minimize the residuals ones to make life more bearable. We are working on the graph presentation side of things in SasView. Some people find the proliferation of graphs a bit irritating. So you can see that it's done a reasonable job. A bit more playing around with some parameters is obviously going to be needed, but it's certainly getting the plateau region of the form factor about right. There's some work that needs to be done here on the position of the fringe in the shell contrast, and the fringes that the calculation has are obviously way too distinct, and that's probably because if we go back to our fit pages, at the moment we have no instrumental resolution smearing in there at all, because there was none in the data file. Now we could, if we want, actually introduce some. This is measured on an instrument with pinhole geometry, so I could select that, and then I could give an estimated value for whatever I think the degree of smearing is, and that would wash out those fringes a little bit. The other thing that would probably help there is if I was to introduce some polydispersity on something like the shell thickness. But again, in the interests of time, I'm not going to go there. Something else I will show you, though, with this data set is what happens if you play around with optimizers. So here under fit algorithms, this is where you can choose the optimizer that's in use. Okay, and as I said earlier, by default, SasView uses the Levenberg Marquardt. I said that was a fast optimizer, but not necessarily robust, whereas another optimizer called Dream was very robust. So I'm going to switch to Dream, and I'm going to ask it, I'm going to click fit on the simultaneous fit page again. Now you can immediately see this is taking a little bit longer, and that's because Dream is actually a slower optimizer. If I bring back the log explorer, you can actually see some of the iterations that are going on there, and you can see at the end of the row here is an ETA. It actually has a go at calculating how long it's actually going to be. There we go, it's now finished. So because it's re-optimized things, it brought back all the residuals plots. But what I want to show you is this results panel that comes back from Dream. This is only available if you use the Dream optimizer. It has 4 tabs in here. So this first one is showing you how the convergence has progressed as Dream was doing its job. Now, here we're actually not seeing any real convergence at all, and that's because we'd already run this through the Levenberg Marquardt optimizer, and we already had something that's a reasonable solution. So seeing essentially something quite flat there is not surprising. The parameter trace is showing us how well the optimizer has been varying different parameters, and what you want to see here is something that looks really messy. So what we're seeing here is good. The uncertainty tab is showing you the uncertainty on the different parameters, and of course a good solution, you would be getting bell-shaped curves, as the statisticians would call it. And you know, I hope with the eye of faith you'll agree that we're kind of seeing that there. The yellow region is the confidence limits. And a really important view that's available is in the correlation tab, where the program will actually show you correlations between your parameters. And what you want to be seeing here is nice, tightly focused spots. What you do not want to be seeing is diagonal lines, because if you see those, that means you've got some really strong correlations between your parameters. So this is very good. It's telling us that we don't have any correlations. We don't have nice, tightly focused blobs here, but you know, as I've said, there's still room to improve this particular fit. What else? Oh yeah, okay, one thing I will show you here. So if I choose a data set, suppose I was going to put some polydispersity into this model. So which one we got here? Let's go for the shell contrast. I can check the box down here for polydispersity. That enables this polydispersity tab. And in this model, there are 2 parameters that can be polydispersed: the core radius and the shell thickness. So if we find that particular data set, and you have a choice of some different distribution functions. These are described in our help documentation. I'm going to leave things at Gaussian for the time being. But you may need to think about whether that's a good distribution to use for some of these parameters. So if I set 10% polydispersity on the radius, it has done something to the curve, and if I do that to the shell thickness as well, you can see it's beginning to wash that fringe out a little bit. I'm looking for another window that should have appeared. You got lost. Let's see if we can make it appear, shall we? So we're just waiting for Dream to do its thing. Let's just stop it. No, okay, that's what I was looking for. Because we've introduced polydispersity into the model now, we get additional graphs because now it actually shows us the distribution function. Now, at the moment, this is looking a bit funny because it's on a log-log scale. So let's change this one to a linear scale. Okay, so there you go. There's our Gaussian distribution. Something to be wary of when you're using distributions is you want to be careful that your distribution doesn't extend below 0, because if it does, that's going to give you some weird results. Okay, so that was simultaneous fitting, and you've also seen what happens if you change optimiser. I'm going to go back to the Levenberg optimiser in the interests of speed. So there we fitted 3 data sets simultaneously. What if you actually have an awful lot of data? So let's clear SasView up again, get rid of these. Close that down. So I'm going to load in another data set, and this time, although I'm only loading in 1 data set, as you'll see, it has a lot of data in it. There we go. Now, I have absolutely no idea what this is. Looking at the way the contents are labeled, things going up to 870 degrees, my guess is that this is actually some thermal annealing data on a ceramic or a metal sample or something like that. I realize it's not soft matter, but for the purposes of this demonstration, it'll do nicely. Because I don't know what it is, I don't actually know what model to fit to it. So I did actually have to do some playing around. And I found that a fractal model wasn't too bad. So I'm going to choose the first data set in here. I'm going to send that to fitting, shape independent, fractal. Let's have a look at the data. So there's the data in blue. So we obviously need to play around with some parameters. Obviously, I've done some of this. So I'm just going to move the fitting range in a bit. Let's go somewhere around there. Let's up the volume fraction. Let's set the size of the primary particles to something a bit bigger. Increase the fractal dimension a little bit. Let's really push the cluster size up. And I have no idea what the scattering length densities are. So let's just go for something like maximum contrast, shall we? There we go. And let's fit scale. Sorry, let's fit the volume fraction in the background. The starters. Okay, and then we can optimize the others. Okay, so we seem to be kind of getting somewhere, all right, for the purposes of this demonstration. Now, if I had to do what I've just been doing on every one of these data sets, that would obviously be rather tedious. Is there a quicker way? And the answer is yes, there is. So what I'm going to do is I'm going to select a bunch of data to fit. I'm just going to choose every other one. There we go. And then I'm going to check this button down here that says batch mode. And I'm going to send the data to fitting. And what's happened is it's created this thing called a batch page. And here's the data that I've selected. And again, you need to choose an initial data set. So I'm going to leave it at that one because that's the one we just did a trial fit on. I'm then going to create the same model. So here's my fractal model. And the neat trick here is I can now go back to that test fit I did in fit page 8. I can go edit, copy parameters. I can then go to this batch page and then do edit, paste parameters, and it gets me to the same place. And then what I'm going to do is I'm going to click the fit button on this batch page. And what's happened is SasView has gone off and it's actually fitted the same model to all those data sets. And here are the results tabulated for me. Okay. And if I want, I can save those to file. Or if I want to see how good a fit was, I just select one of these and I click plot. And you can see it. So that's batch fitting if you've got lots of data. If you really had a lot of data to fit, or it was a really complicated model, something you might want to consider if your PC or your Mac allows it, is to actually, rather than using the CPU, your main processor, is to actually use the graphics processor, because those are designed to be a lot faster. And SasView will use compatible GPUs. So under fitting, there is GPU options. And you can see on this laptop I'm using, I only have two options. One is what it says, no OpenCL. That basically means just use the CPU, but it has recognized that I've got a on motherboard Intel graphics chip, which is actually compatible with this framework called OpenCL. And because SasView is also OpenCL compatible, what I can do is I can actually use my graphics processor to actually speed up the calculations when I'm doing optimization. If you don't know whether your GPU is compatible with SasView, or you have more than one GPU option, and some people do for various reasons, what you can do is you can click this test button and SasView will actually go off and it will try compiling various bits of code on your GPU to see whether it's going to work, and it will give you a result, so that you can decide what you want to do. Okay. Thus far, let me get rid of all this data. So select all, delete data. This will take a moment. Oh, okay, that's quick. I'm just thinking about it. Drilly hourglass. There we go. Okay, so far we've only fitted 1D data. SasView can fit in 2D as well. So I'm going to load in a 2D data set and send that to fitting. Oops, sorry, I've still got batch page checked. So let's uncheck that and send it to fitting. There we go. So this is data from a ABA block copolymer, something called Pleronic P123. I think Otto showed some data from P94. So this is another one of the family. And it's in D2O and it's at 10 weight%. So it's fairly concentrated. So again, we have micelles. So we'll guess that they're going to be spherical micelles. So let's have a look at the data. And now, rather than getting graphs of intensity against Q, what we're actually getting is intensity in color against the components of Q parallel and perpendicular to the beam. So that's a residuals plot. So I'm just going to move that one out of the way a bit. So just like we did with 1D, we can fit a volume fraction and the background and the radius. If I knew what the priors were for this, I'd put them in. And I can click fit, and SasView goes off and does a fit. And if I wanted, this is 10 weight%, maybe it wouldn't be a bad idea to actually introduce some sort of structure factor. So I'm going to turn off the scale because we now have a volume fraction. You know this is 10%, so let's guess it's going to be about 0.1. We're tying the micelle radius to the radius effective, again, like we did before. Okay, and let's see what happens now. Okay, now you might be thinking, that calculation doesn't look much like the experimental data, but hang on a minute. If I right click on the plot, I can choose 2D color map. Let's put these on the same color scale. Okay, so hopefully now you'll agree that actually maybe they aren't quite as dissimilar as you initially thought. So you can do 2D fitting in SasView. When you're doing 2D fitting, you can also do some derived 1D plots using what we call slicers. So if you right click on the plot, it gives you the option for some various slicers. So for example, you can do sector slices. So what it's doing is it's integrating the intensity as a function of Q between these two outer sector limits. Okay, and what you can do is if you grab the middle one, you can move it around. This is isotropic data, so I don't expect the plot's going to change very much. And you can grab one of these and you can change the width of your sectors as well. Or you can do things, so I clear that one. Or for example, you can integrate the intensity in a ring. So this sort of thing is great if you've got anisotropic data, or if you're trying to find out if your data is anisotropic. So those are some useful tools. There are also some slicers in there that draw boxes and tell you what the average intensity is in those boxes. So that's fitting 2D data. I mentioned at the start of the first session that here at ISIS, we not only have SANS instruments, we also have something called a SESANS instrument, a spin echo SANS instrument. There aren't many of them in the world, but there's one at Indiana, there's the one here at ISIS, and there's one at Delft in the Netherlands. And spin echo SANS is a way of accessing very long length scales, but without having very long instruments, which obviously kills your flux. What you do is you actually encode the very small scattering angles in the Larmor precession of the neutron. Remember, the neutron has a magnetic moment. So what I'm going to do is I'm going to load in a, let's clear everything first, sorry. So I'm going to load in a SESANS dataset. And we've set SasView up so that if it finds a file with the extension .ses, so just something we invented, it's going to assume it's SESANS. I can then send that data to fitting. Now, the name of this file is actually giving things away. It says it's 2 micron spheres. So I guess we're going to need a spherical model again. Okay. But if I plot the data now, rather than getting intensity against Q, I'm getting a normalized polarization as a function of spin echo length Z. Okay, and this is a major difference between SANS and SESANS in that SESANS works in real space, which confers some advantages. There are a few disadvantages too, but it's kind of complementary to standard SANS. But I can fit the data in exactly the same way. So we have a bit of a priori information here because we know these are 2 micron spheres. So 50 angstroms is obviously going to be a bit low. So let's shove that up to something rather larger, shall we? And let's fit a volume fraction and a background and a radius here. And there you go. SasView has actually fitted the SESANS data, because what it does is it takes the model calculation and performs what's called a Hankel transform to go from reciprocal or Q space through to real space or Z space. So it does that on the fly. So we can fit SESANS data. But SasView is even more versatile than that. Those. Okay. But it is nothing more than a fitting engine, so you can fit essentially any old data. So just to demonstrate that, here's some DLS data. Now, of course, none of the standard models in SasView are going to be any use for fitting a DLS correlation function, but on the model marketplace, somebody I know produced a model to do cumulance analysis. So I've downloaded it from the model marketplace, installed it in my SasView plugins folder, and the model is available to me. Okay, and you can see it allows me to set the scattering angle and temperature, all those things that are used to derive the size. If you want to look at the data, there we go. So here's the correlation function. Most of you will be more familiar with seeing it with a linear y-scale, something like that. So SasView doesn't know what this data is, okay, which is why it's labeled it as intensity against Q, but we know it's DLS data. So actually what you have here is correlation function against delay time. What I'm going to do is I'm going to move this bar into, well, let's move it into about 10 microseconds, shall we? And we'll move this one into about 0.1 of a second. And essentially what we want, we'll assume that the experimental parameters are all correct here. And of course, what we want to fit is how big is the microgel particles. We'll fit the background and we'll fit the correlation function intercept. And there you go. So I'm fitting non-neutron data in SasView there. So I've given you a pretty big tour of model fitting there. So the question that arises, of course, is what happens if the model you want isn't available? Well, the first thing we would say is, are you sure? So go and have a look. Is this going to work? Yeah. Go and have a look at our list of models and see whether what you want is there or not. If it isn't, go and have a look at the model marketplace that I showed you before lunch. But what if that still doesn't meet your needs? What you can do then, or the first thing you can do is you can actually combine existing models. And we have a little tool that does that. So here under fitting, I can go add multiply models, and I can create a plugin model. So I'm going to give it some name. Let's call it Steve. Some title. And let's say we want a model that combines a power law with, I don't know, power law and a sphere, let's say. There we go. And we can choose whether to add those models or multiply them together. Normally you would add them unless one of these models was actually a structure factor. And then I can click apply. And then if I look in the plugin models category, I'm hopefully going to find, there we go, a model called Steve. Okay. And the power law parameters, it's prefixed with A, and the sphere parameters, it's prefixed with B. So that's a quick way of combining two models. What if you want to combine more than two models? Then you can go into fitting and you can go to edit custom model and you can load in your plugin. So let's go find Steve. There it is. And I don't know why you might want to do this, but let's say you wanted to combine the power law and the sphere. Let's do it with a cylinder, shall we? Cylinder. There we go. I can save that. Now, word of warning, it overwrites the model that we had there before. Because I already had Steve loaded into the fit page there, you might have noticed something just happened. And what's happened is that it's added on the cylinder parameters at the end. So again, we have the power law parameters prefixed with A, the sphere parameters prefixed with B, and now we've got the cylinder parameters prefixed with C. The other way you can do this is you can use an external editor. So if I go to my plugins directory, hopefully you're seeing this, please shout if you're not. I can find that plugin. I can right click on that and open it in an editor. There it is. And if we say to ourselves, oh, I made a mistake. I didn't want to add in a cylinder. What I really wanted to add in here was an ellipsoid. Okay, you can then save. Now, because I did that outside the program, SasView doesn't know about it. So I need to, if you like, force this fit page to refresh. So you can do one of two things here. You could either go fitting and create a new fit page, or the other thing you can do is just navigate away from the plugin that you had there and choose something else, and then go back to the one that you actually want. It's not showing all the parameters for some reason. Let's try a new fit page. I don't claim that SasView is completely bug-free. Every now and again, you might find something. If you do, please let us know. Okay, that looks better. Okay, so again, the power law parameters are prefixed with A, the sphere parameters are prefixed with B, and now the ellipsoid parameters are prefixed with C. How do I know those are the ellipsoid parameters? Because rather than having a radius and a cylinder length, I now have the polar and equatorial radii. So I know that it has actually changed that. What about creating a model from scratch? Well, there's three ways of doing that. If it's a fairly simple function you want, then you can go into fitting and you can do add custom model, and it brings up this model editor. So we can create a new plugin here. So I'll call it Steve 2. Again, I can give some title. So let's say we wanted to fit a quadratic function. So we all know the formula for that. So A times x squared plus b times x plus c. Okay. But if I try and apply this, I get a red box. And the reason I get a red box is because, as it's telling us, we haven't defined what A is. Equally, we haven't defined B or C either. So we have to give it some default starting parameters. So I'm clicking there and I'll type parameter A, will give the initial value 1. Parameter B will give an initial value 2. And parameter C will give an initial value of 3. Apply. Cancel that. So if I create a new fit page, again, go to my plugin models. Now I should find there is Steve 2. There we go. So now I'm using SasView in calculate mode because I don't have any data loaded. So I can go calculate, show plot, and there's my quadratic curve. If I change some of these parameters, and if I put this up to 4, for example, it changes the shape of the curve. So if you have a reasonably simple function, you can use that add custom model method. Another way of doing it is what you might call the variation on a theme method. So all the models in SasView are in a folder called models, which is a subfolder of SAS models, which is a subfolder of the installation directory that you installed SasView into. So if you think there is an existing model which kind of does what you want, but maybe you just need to subtly alter it, then what you can do, and I'll choose the correlation length model here because it's a kind of simple model, is you can take a copy of that and you can paste it into your plugins. Then, very important, change the name. Because otherwise you're going to confuse SasView because it's going to find it's got two correlation lengths models, so we'll call this C3. And then you can edit the code. But now you're really editing some serious Python. It's still not too bad for this particular model. There is much more detail about this in our help documentation, but basically this section in orange is a description of the model, which, if we incorporate this model into SasView, becomes available in the online help documentation. Here's the name of the model down here, so we better change that, otherwise we won't be able to identify it. Okay. Here are the parameters in the model. We can either add to those, or we can remove, or we can change the names and do whatever we like. And then this section here is the bit that's actually calculating our function. So you can see what's being returned is this variable in10 for intensity, which is a sum of those two bits, Poirot and Lorentz. And there's the definition of Poirot and Lorentz. So this is a fairly simple example. You don't need to know too much about programming to figure out what's going on in here, okay? And the bit at the bottom here is basically a collection of Q values and calculated intensities, which, if you specify them, then when SasView loads the plugin, it runs the test just to check things are going to work, which is quite nice. I don't have time to do anything really clever in here, so what I'll just do is change the name of a variable so as you can see that it actually has. I'll do this Steve exponent. So I then save this particular model. We can go back to SasView. Doesn't really fit page to be certain. It would be under plugins. Called it Steve 3, and there you go. You can tell that it's the one that I've just edited. So if you can find an existing model which is close to what you want, you may be able to edit it a little bit. If you can't, if you've suddenly found some wonderful equation in a paper somewhere that you want coded up and you can't code it, I'm afraid you're going to have to find yourself a Python thing. Whilst the development team would love to do it for you, we simply don't have the resources. So that's finding models. So my time is fast running out. What I would like to do to just finish up is to show you some of the other things that you can do in SasView. So here under analyses, you have the various things that SasView can do, okay? And so far I've only shown you fitting. So why don't we start at the top and work down? So the first one is correlation function analysis. So I think Otto touched on this in his talk. A correlation function describes how the probability of observing some physical quantity varies in time or space relative to some reference. A temporal example many of you are going to be familiar with is the intensity correlation function from dynamic light scattering, which is quantifying how the coherence of the scattered light is changing with time as the particles are undergoing Brownian diffusion. A spatial example that Otto showed was a pair correlation function or a radial distribution function when he was talking about structure factors and coordination shells. In a small angle scattering experiment, the scattering we observe reflects the arrangement of regions of similar scattering length density, or by inference, similar bulk density, since the two are related. So we're effectively measuring a density correlation function, and we can extract that from the scattering data by inverting the Q space data into real space, and that's what correlation function analysis will do. So if I load in a data set, and I'm going to load in this one, and then down here at the bottom, instead of send to fitting, I'm going to say send to core func. And the data appears. Now you'll see there's a nice peak in the data. This particular data set is from polyamide 6, otherwise known as nylon 6. And the thing about nylon and other polyamides is they are semi-crystalline polymers. So they have crystalline regions joined to amorphous regions, and that repeats throughout the structure. And so actually what you've got is a sort of linear in a linear form, you've effectively got a quasi-lamellar structure in there, and that's what's giving rise to that peak. So that's actually a diffraction peak. Yeah. Now, to extract the correlation function, you actually need to invert the data between q equals 0 and q equals infinity, because we don't measure over that range. So the first thing we actually have to do for the analysis is we have to extrapolate our data in those two directions. And we do that by applying a Guinea extrapolation at low Q and a Poirot extrapolation at high Q. At the moment, that's all you can do. It may not be what you need in all circumstances. So the first thing I'm going to do is I'm going to set some range limits to define the extrapolation. So I'm going to do the low one first, and with some values that I've already played around with. It seemed to give a reasonable result. Go. And then, as Otto was saying this morning, when you're inverting things, it's important you accurately assess your background, so the program can do that for us. So I'm going to say calculate my background. There we go. And then I can click the extrapolate button to do the extrapolations. There we go. Having done that, I can then click transform, and in the bottom window, my correlation functions appear. It's given me two, a 1D correlation function and one that's averaged over all three dimensions as well. So this particular sample was a nylon fiber held top and bottom. So the 1D correlation function is this density correlation function running along the length of the fiber, which is why the peak in there is much more pronounced. Now, this inversion of the data is general for small angle scattering. I've successfully used it on some metal alloy samples as well, and we did a comparison with an analysis that had been done with atomic probe tomography and got pretty good agreement. If your sample is lamellar, or at least quasi-lamellar, then you can go a step further, because there are various publications that look at the slopes of these correlation functions and the positions of the peaks in them and the positions of the minima, and use those to interpret things about the quasi-lamellar structure. So I can do that in this case. So I just click the extract parameters, and there we go. So it's telling me, for example, that the long period, okay, the spacing of the crystalline regions in here is about 74 angstroms. And it's even given me an idea of what the degree of crystallinity is. So if you want to know more, go and read the help in our documentation. But that's a demonstration of correlation function analysis. There is still work to do on this interface. That's why the plots aren't appearing quite like the ones from fitting. So things may gradually change over time, but the functionality is there and it does work at the moment. The other thing, the next thing we can show is actually P of R inversion, which is what Otto was showing this morning. So I need a suitable data set for that. So I'm going to load in a protein. So this is loading in data from conalbumin, which is the iron binding protein in hen egg white. So I'm going to send that to inversion, this panel. There we go. So I don't think I need to explain what P of R inversion is all about, except to say that the way that SasView does things under the hood is subtly different to the way that Otto was showing this morning. But at the end of the day, they ought to give, I would hope, similar answers. If you're listening, Otto, maybe we should try this one day. So here in the middle, we have some parameters which are controlling the inversion process. Okay, And in the boxes, we have some starting values. And over here on the buttons, we have some suggested values that the program is making based on looking at the data. And if you click the button, it will set the value in the box. Okay. In options, again, we can vary the range we want to do things over, and we can either manually set a background level or we can let the program estimate it. There is a little bug at the moment in that when it estimates, it's not showing the background level. We are aware of that one. So if I click calculate, there we go. So what you're seeing now is not unlike what Otto was showing this morning. So here's the P of R curve, and the orange line is the fit to the data. Well, we can see that we can probably move this in a bit, move the low Q limit in a bit. We can recalculate. And you kind of iterate around things here until you get a good solution. One that Otto was talking about the need to make sure that you are doing your inversion over an appropriate size for what is actually scattering in there. And the way we have things implemented here, we have this nice button called Explore, where you can plot some various parameters as a function of the maximum distance of the inversion. Okay, and the one that we have selected at the moment is the chi-square. And you can see at the moment that the maximum distance we have set is 140, which is out here, but actually a smaller maximum distance looks like it would be better. What we can do in this little widget is actually see how much lower or larger, if that were the case, we have to go. So if I set a smaller value in there, aha, okay, we actually find there is a minimum in the chi-square down here at, I don't know what, maybe about 92 angstroms. I could play around to zero in on that if I wanted. So I can set a smaller maximum distance in here. Now, the observant amongst you will have noticed as soon as I did that, this regularization constant, the suggested regularization constant changed. So I need to reset that. The number of terms hasn't changed, and then I need to recalculate. And now I'm starting to get a smoother P of R curve, which is one of the things that Otto was talking about. And to know whether I'm getting a good solution, of course, I can use some of this other information here. So for example, if I've done a Guinea plot, I could see whether the RG that I'm getting out here kind of corresponded to what I got from the Guinea plot. Or alternatively, if I know my contrasts, I could use the I0 value here to calculate the molecular weight and see whether that made sense and it was anything like what I got out of ultracentrifugation. So that's P of R analysis. And the last one I'll show you is just the invariant analysis. I'll just pick one of those emulsion data sets for that, and I'll send that to invariant. Let's get rid of these. So send it? No. Okay, send it. There we go. So immediately it calculates an invariant for me, and the invariant is the integral under the scattering curve. For the numbers here to have any meaning, you really need to put the actual contrast in. We deliberately put what we think is a largely unphysical contrast in there, but I know what it should be for this one. So then I can recalculate my invariant, and because I've given the contrast, it will actually calculate the volume fraction for me. However, again, what you really ought to be doing is measuring. If you can't measure your data over a big enough Q range, then you're going to need some extrapolations. So let's do some extrapolations again. Or didn't that rotate? There we go. So here you see the experimental data in green with the extrapolations added in, and that's now changed the invariance slightly, which means the volume fraction that's being calculated has also changed. This status button brings up a little view which shows you how much of your invariant is coming from your data and how much is coming from your extrapolations, which can be quite useful. Again, if you want to know more, please read our help. And very last thing is just to show you that we have a range of tools in here. You can manipulate data sets, you can calculate scattering length densities. If you have coordinate data like PDB files, for example, you can actually generate the scattering pattern, calculate it from the PDB. If you really want to interact with the SasView API, there is a Python shell you can open up to do that. You can load in image data. I haven't got time to show you that, but if you've got a JPEG or a PNG or a TIFF file or something like that, you can load it in. And if you happen to know what Q range your image data corresponds to, you can actually generate some pseudo data and go off and fit it. And there is a file converter in there which will convert a couple of really old formats that are still in use in one or two places into more modern formats, so that you can then access those in SasView as well. So my time is virtually up, and I want to leave some time for some questions. So thank you very much for listening, and I guess I should also thank the other members of the SasView development team for their forbearance. One or two of them lent me some slides, and it's a great collaboration to be part of, and we've had a real ball over the last 8.5 years. So I'll hand back to you, Yang Yang.
Thank you, Steve. Thank you for the wonderful demonstration. We have a question from Greg. He's asking whether SasView can do Fourier transform of the image in the image view.
No, not at the moment.
Okay. So I'll
write that down.
Yeah, I wonder if you could share with us the data you use in the demonstration, so that you know, we can play with the data and see how it really works in SasView.
Yeah, so all of the data I've showed apart from the DLS data is in the test folder that you get when you install SasView.
Oh, okay. Okay. Yeah. Thanks. So I also wonder if you know, if I have a existing workflow of data analysis in Python, is it possible to? Is there an easy way to use all the modules in SasView without using the graphic user interface?
Yes, so you can. It is possible to run SasView headlessly, as we call it, and in fact, at the Diamond Light source, they kind of do that routinely. So if you're really interested in that sort of thing, I can put you in touch with the guy there that's done that. I thought that Matt Doucet had done something similar at SNS, so you might want to check with Matt first.
I see. So there's no easy way to do this. So we really need help from experts.
I mean, basically, it means it just. I'll say just, but it basically just means calling. Basically, you would use SasView as a library, and you would just call that library from your Python script. Okay,
I see. All right. Any other questions from the audience?
Yang, I saw one question to me. Actually, okay. I can read that.
Sure.
Can you please explain one more time the purpose of changing the weighing? Is it applicable for membranes as well?
Changing the weighting.
Weighting. I believe it's a weighting. Yeah. So that's a type of. Yeah.
Yeah. So In an ideal world, hopefully your reduced data always includes Q, the intensity, and the uncertainty on the intensity. That's what it really ought to have. If you get the uncertainty on Q as well, even better. Okay. So all I was demonstrating was that if you don't have the uncertainty on the intensity, you are going to get a different fit and therefore different fit parameters to if you actually had the intensity. And if you, the uncertainty on the intensities. And if you don't have the uncertainty on the intensities, there is that little trick you can do in SasView to actually fake, if you like, that you have them there. But the essential point is, if you don't have the uncertainties on the intensity and or Q, you are going to get a different fit, and you need to remember that, because that might be important.
All right.
Don't know, did that answer the question?
Yes, yeah. I am the one who asked the question. Yeah, it answered. Thank you. Thank you so much.
You're welcome.
All right. If there are no more questions, I'd like to thank Steve again for the wonderful demonstration and the lecture. We're going to have a short break, and we'll be back